All right, we are recording now. We're looking at section 11.3, partial derivatives. And, okay, so you know how to take derivatives when you have a function of one variable. How do you do derivatives when you have a function of two variables? Okay, it's quite interesting. So let me find the definition. Actually, this isn't it yet. Let me go here. I want to just get down to here. So we have partial derivatives. Partial derivatives. So you have a function of two variables, and you can, like in the first definition there, f sub x, that stands for a partial derivative of the function with respect to x. And that means you hold the y constant, but you let x vary. So you see there, you have in the numerator, so in the denominator you have h, and you're going to let h go to 0. You're used to that. In the numerator, you have the difference of two function values, but one is f of x plus h comma y, the other is just f of x y. And then the second definition, you're letting is the partial derivative of f with respect to y, f sub y. There, you're holding x constant and you're letting y change. Okay, and if you want an interpretation of these partial derivatives, I'll show you here. Let me go. Hold on here. I want to go here to the picture. So here is a surface, and you have a point on the surface at with coordinates a, b, and c. Okay, x, y, z coordinates a, b, and c, and you have two tangent lines. Tangent line 1 goes in the direction of what axis? In figure 1, that first tangent line to the surface points or goes in the direction of what axis? The x-axis or the y-axis? The t sub 1, t sub 1. It goes in the direction of the x-axis. At least unless I'm looking at figure 1, I want to make sure I'm. So let me ask you this. Let's do this. Okay, because I have intelligent people who are interpreting this differently, and you know, I want you to all think the same way on this. Thank you for your answers, everybody. Yeah, so you see the, that's right, Lexi, you see below the tangent line, there's a C1 curve, a space curve C1. You see that? That blue space curve C1? It's on the surface. That's right, and that space curve, the points on the space curve, x changes, but y is constant, right? Y is some value. So the tangent line to the space curve at the point ABC, that t sub 1 tangent line, it's parallel to the x-axis. However, if you look at the second tangent line, t sub 2, below it is space curve C2. That's a space curve on the surface. So you're holding in that case, you're holding the variable, x constant, and you're letting y vary. And the tangent line T2 is parallel to what axis? The tangent line T2 to the surface at the point ABC is parallel to what axis? X or Y? That's right, Norina. That's right, Lexi. The Y-axis. Okay, so let me just okay, everybody's good with this, hopefully. So these tangent lines, then they have slopes. Okay, that tangent, that T1 tangent line has a slope in the direction of the x-axis. It has a rise and a run. Rise over run equals the slope. And the tangent line T2, that has a slope in the direction of the y-axis. That's called, that's your, that would be your, so I want to say this again. The tangent line T sub 1 has a slope in the direction of the x-axis. That's your partial derivative of f with respect to x. The tangent line T2 has a slope with respect to the y-axis, and that slope is the partial derivative of f with respect to y. Okay, so that's essentially geometrically what the slopes, what these partial derivatives represent. Okay, so I think that's hopefully helpful. And if we wanted to here, if we wanted to talk about notation, there's a lot of notation for partial derivatives. Okay, so when, maybe let me just highlight this. These are all the different kinds of notations that you can see when you deal with partial derivatives with respect to x and with respect to y. These are all the partial derivatives that you can see. So you have Leibniz notation that uses those. So like, let me just go to the whiteboard here. Okay, so you have, this is Newton notation. And with the scripts here, this is Leibniz's notation. So back when you studied calculus 1 and 2, you know, you had f prime of x, right? That was Newton's notation. But that could be thought of as df dx, right? That was Leibniz's notation. So similarly, for multivariable calculus, you'll have Newton's notation and Leibniz's notation. Okay. So let's look at a very well. Okay, what are the rules now? What are the rules now for computing these partial derivatives? Let's go back to the book. Hold on here. So you'll be happy to know that all the rules that you learned for derivatives are going to apply here. But what you have to be careful of is, if you're going to find the partial derivative, like here's rule 1, if you're going to find the partial derivative of f with respect to x, remember, you're finding the slope of a tangent line to a surface at a point in the direction of the x-axis. So y is held constant. You just differentiate with respect to x. On the other hand, if you're finding the partial derivative of f with respect to y, that's the second rule, then that partial derivative is the slope of the tangent line to a point on the surface in the direction of the y-axis. So you're letting x be constant, and so you differentiate with respect to with y. So let's look at a very simple example here. I'm going to go, I mean, we will get into more examples, but let's look at actually a few simple examples. Okay, so hold on. I want to try to highlight this if I can. Yeah. Okay, so here they say, okay, our function equals x cubed plus x squared y cubed minus 2y squared. Find these first partial derivatives at the point 2, 1. So when x is 2 and y is 1, find the slope of the point on the surface that has those x and y values. One moment. Okay, so you see what they do here in the first part. You see how they treat the y like a constant. Okay, so when you find the partial derivative of x cubed is 3x squared, but then I'll tell you what, let me go to the whiteboard on this one. This is example 1. Let me go to the whiteboard, and I think I can maybe do this in a little more detail for you. Okay, so why does that? Come on. There. So this is example 1 from section 11.3. Our function is x cubed plus x squared y cubed. Sorry, I gotta write it well. Minus 2y squared. And what we're looking for here, first off, is the partial derivative of our function with respect to x. Okay. Now, we can think of that like this. Okay. Take the partial derivative of the function with respect to x. Now, what we can do, of course, is we can break this up into little pieces, right? The derivative of a sum is the sum of the derivatives. Please let me know if you have any questions. I'm putting in a lot of detail for you. Okay, and remember, we treat y as a constant. Because we're differentiating with respect to x. So far, are we good up to here? Are there any questions? All right, very good. Let us proceed forward. So the derivative of x cubed is 3x squared. Now, for this second part, the partial derivative of x squared y cubed with respect to x, we can bring y cubed out in front because it's treated like a constant. If y is a constant, then y cubed is a constant. So you can bring it out front, and you have this. See that? The third part, the derivative, the partial derivative of 2y squared with respect to x, well, that would just equal 0 because we're treating y like a constant. So 2y squared is a constant. If you differentiate a constant, you get 0. So what you're going to end up getting is 3x squared plus, well, the derivative of x squared is 2x. So 3x squared plus 2xy cubed. See that? And so this means then that the partial derivative of x, partial derivative of the function with respect to x at the point 2, 1 would just be 3 times 2 squared plus 2 times 2 times 1 cubed. And that, let me see, what does that equal? That will equal, gosh, what does that equal? It's equal to 3 times 4 plus 4 times 1, 16. And that matches the book answer. That matches the book answer. See how that works? Now, if you were to do the, well, are there any questions on that? All right, then let's do the next one. Let's do one more here. Okay, let me do that. I'm going to go ahead and I'll have to clear this, I'm afraid. But let me just go ahead and do that. It's in the recording. Hopefully you're good. Let's do the last one here. This will not take long, class. So again, our function is x cubed, and I'm going to move kind of fast here because I know we're at basically 9:30 here. X cubed plus x squared y cubed minus 2y squared. Okay, again, we're looking at example 1, section 11.3. Now we're doing the partial derivative with respect to y. Okay. So we're differentiating this whole thing with respect to y, this whole function. And this is naturally the kind of work I would want to see on your exam. You're just learning this, so there's work to be shown. Right? All right, so partial derivative of a sum is the sum of the partial derivatives. And here now, we are treating, here we're treating the variable x as a constant. Because we are differentiating with respect to y. So we treat the x as a constant. So that means that the partial derivative of x cubed with respect to y is 0. Because what's the derivative of x cubed is, if x is a constant, x cubed is a constant. So you get 0. And then for the second part here, well, we can bring out the x squared, because that's a constant. And then this is just 4y. So I hope this is all good. And we're going to end up getting 3y squared times x squared minus 4y. Okay, 3y squared times x squared almost done here. 3y squared times x squared minus 4y. And if you evaluate this, if you evaluate the partial derivative of y at the point 1, 2, we get, do we get 8? Let's see, that's 3 times 1 squared times 2 squared. Let's finish this up here. Minus 4 times 2. So that equals 4. And that is, no, wait, no, I'm getting 8. Hold on. I'm doing something wrong here. I'm doing something wrong. It's not 1, 2. It's 2, 1. See, I'm worried about the time. But I think you all can stay at a minute, a few extra minutes. 2, 1. So let me fix that. So that's 3 times 2 squared times 1 squared minus 4 times 1. That is 12 minus 4. That does equal 8. You were right, Norina. You were right. So that all equals 8. That all equals 8. Okay. Are there any questions on this before I stop the recording? Any questions at all here? Hold on here. Okay, so then, there we go. Class, I do thank you. Thank you for a great class tonight. We'll continue section 11.3 on Thursday. I will take the password off though if you want to look ahead on it. Thank you for a great class, everybody. I will stop the recording here. Excellent.